Okay, something just clicked off. That was weird. Can you all hear me? Okay, so, yeah, radio's having issues. Okay, hi, and so a couple things going on. Um, David, would you throw me that pack of tubing there?
Throw you the what?
The pack of tubing right by the microphone. Yeah, I need him. Thank you. There's a story here. You'll appreciate this story. We did a reactor experiment in which we looked at flow and heat, and we didn't get exactly the outcome that we wanted. And we ran the reactor. What for reactors is actually quite very cold. And then we looked at a couple of flow rates, and then we ran the reactor at a very high temperature and a couple of flow rates, and we saw in the high temperature a lot of instabilities. What you folks don't know is that after you left, we had a reactor leak. Water started coming down the reactor vessel and into the electronics in the bottom of the reactor. In case you don't know, water in electronics is not a good thing. No, you don't want to go there. So I didn't have time to deal with it then until the weekend. So we did Dave's presentation last week, and over the weekend I got into the reactor and started looking, and I found this leaky hose connected to the heat sink on the front con flat of the reactor. So I cut it off and got a fresh piece of PVC and put it up and connected it. Then I fired the whole thing back up again and turned on the cooler, and I see water coming around the tray of the computer. That's not right. So then I go around behind the reactor, and I've got two leaking hoses on the back heat sink. Well, to make a long story short, PVC melts at temperatures of 120 or so. We were up at 160. So basically we melted all the tubing off of the cooling system on the heat sinks of the reactors. Again, not a good thing to do. Luckily it didn't gush. It dripped. So it didn't damage anything in the reactor. We got it all wiped up and dried out, and that all worked fine. But this is not PVC. This is silicon, and silicon is good to about 500 degrees F. So what we're going to do is we're going to attach some silicon everywhere it touches the reactor vessel. PVC isn't such a bad thing back further downstream, but it cannot come in contact with the reactor vessel because we do occasionally run it at high temperature, and we found out the hard way what happens. Real world. Anyway, neat story. We will not be meeting either Thanksgiving week or Christmas week, either one of those. So next week we are off. Go enjoy your family. We'll pick up the week following and go on from there. I think that pretty well covers my announcements. So we have David up tonight. He's going to be teaching some chromatography. No, I do have some more announcements. I got a new toy. This is a A2ME Production Studio 4K. This is a serious studio switcher. So we are planning the week of Thanksgiving to do a complete studio revamp, and we are also going to get a motion picture grade camera. This is a true 4K DCI 4096 by 2160, not the typical 3820, which is your ultra high def. This is one step beyond that, and it has a whole lot of really neat features. And we'll be talking a little bit more about why this is important and why we're upgrading the studio at this time. We also have some other bells and whistles, but I won't go into it. We will take you on a tour of the studio once we have it fully built out, and you can take a look at what we've got. This monitor over here, which you can't see because I'm pointing at it, but it's off screen, is a 55-inch ultra high def monitor now, 4K. So things are coming along to give us a really crisp picture. And once that switcher goes in, you won't see things like my headphones are buzzing right now. You can see the sparkles. That's not Christmas, that's just my headphones. Anyway, David, you're up. Come on up here and amaze and saturate our students.
Well, hello everyone. Wanted to let you know, looks like we've got 13 of our 16 in attendance tonight. Realize that unless you notify Carl ahead of time, that counts against you. And also, we had 6 people turn in the last assignment. Another 2 people turned it in late, which I'll live with that. But that means that a lot of you did not turn it in. So you need to make sure you do those when they're sent out to you. Each time I email them to you. Tonight, I'm going to be talking about the periodic table, but we decided we wanted to work in a lab, so we're going to do paper chromatography lab, as it says on the title there. This is a lab that has you set it up and then you have a long time to wait. So we'll set it up and then we'll go ahead and do the lecture on the other, and then check it at the end if it finishes, hopefully. Nope, we're not. So the rationale of the paper chromatography. It's one method that can be used to determine the purity of a substance. If you have a mixture of different things in a liquid, you can do paper chromatography on it, and it can separate the things so you can see what's there. Nowadays, modern labs don't really use paper chromatography. It's basically used by teachers to teach their students about chromatography. And instead, they use thin layer chromatography, where they use a glass plate that's covered with certain salts, and it gives much better results. And then sometimes, even with paper chromatography in the past, they would use it to separate materials in one direction and then turn the plate and separate in another direction. And that especially works well with amino acids. two important words are solvent and solute. A solvent is something that does the dissolving. And a solvent is used in this lab to dissolve a sample on paper and then have the solvent move through the paper due to the capillary action in the molecules. The dissolved material is called the solute. And the solute will separate into its component parts, and that separation is based on solubility. And the solubility is based on the polarity of the molecules. Now, if you use water for paper chromatography, you have to use water-soluble substances, but water is extremely polar, so you can get really good results. But we're going to use 70% isopropanol because I wanted to use different colored permanent markers, and the alcohol will dissolve those. So you'll use 4 different markers. You'll have to have a pencil, and it says a cup, and I did the lab earlier today and found out it's too slow. So instead of the cup, we're going to use real small beakers, 50 milliliter beakers. And then you use a coffee filter. That's the paper that we're using. It works quite well. There are specialty made chromatography papers, but I didn't have those. And then you make a wick from chromatography, from the coffee filter also. And you have to have a ruler. In the procedure, you start by making a very, very small slit in the center of the coffee filter. Then you use a pencil to draw a small square around the center of the coffee filter. Very small. And we use the pencil because pencil graphite will not dissolve in the alcohol, so it stays put. Then in the middle of one side of the square that you just made with the pencil, you make a small dot with a black marker. And everybody's going to use black. And then you let it dry, possibly blow on it, that might help. It just takes a couple seconds. And then you're going to repeat that 3 more, that should say drops. Okay, but 3 more times you're going to make a dot. Same dot, one on top of another, to get more substance on the paper, so it'll work better. And then using the same color marker. Then you're going to do this exact same thing, but with different colored markers, and you get to choose what color you're going to use tonight. And you put a different color on each side of the square. 4 colors, 4 sides to the square. Then you'll use your pencil to label what the colors are that you put on there, so you can keep track of that. You put the tip of the wick in the slit that you cut into the coffee filter in the center. That you want the wick to touch the bottom of the beaker that we're going to use and come up through the coffee filter. And what I like to do is scrunch it up so that it can't fall back through. I've had students have that happen, and that messes up their lab. You put about 30 milliliters of alcohol into the cup. Does not have to be accurate. Into the beaker. You then wait. The alcohol will move up the wick, move into the filter paper, and start spreading out. And as it does, it'll dissolve the ink dots, and they will migrate towards the edge of the filter paper, the coffee filter. When the alcohol gets near the edge, then you remove the paper and you let it dry. Being alcohol, it doesn't take long at all. You then measure the distance the alcohol moved from the square. The square is considered the stationary point, and then you want to know where it moved to, and also where the alcohol moved. There'll be 2 distances measured for each color. Then you're going to do something called calculating the RF for each of your colors. RF stands for retention factor. And you take the distance traveled by the solute, what was dissolved, and divide it by the distance traveled by the solvent, how far the alcohol reached out on the filter. Are there any questions on that before we get started? All right, we're going to go to the lab then. Pull the chairs out, 2 on each side of the table, and pull the table out further if you need. The wick is made simply by taking some filter paper and cutting a triangle in it. And that's your wick. So each of you needs to take a piece of that filter paper, coffee filters, cut a very small slit in the very center of it. I fold it in half. Makes it easier to find the center. Fold it in quarters if you want. That'll make it even easier. And it's like about 1/8 of an inch slit in the middle. Very, very small. Very, very small. I think that's good. Okay. Now, you don't want to put the wick in yet. Pardon? Well, I can't see the slit, but I believe you that it's there. Oh, and there's the written procedures. There's copies for everybody. So what's the next thing you need to do? I started out with 4 pencils, but unfortunately the tip broke off one, so you'll have to share.
How small should the square be?
Like a 1/2 inch on each side. And what's the next step? Yes, I have a few markers. And I suggest go ahead and get out all 4 colors and then as you do each one, by the time you get done with one, it's probably dried enough. You can go ahead and start going around again. Why do you think you're making your dots 4 times? Each dot, each color is 4 times.
So there's more ink?
Yeah, you're trying to build up the layers. You're trying to get as much ink on there as you can so that you'll be able to see it when it moves. Now, those of you watching at home, this is something you can do on your own. And if you don't have alcohol, you could use water. It'll work just fine. But with the water, you'd of course have to use water-soluble inks. What's the next step? If you don't remember, you can always look at the procedure sheet.
We have to make a wick and put it in the...
So each person needs to cut out a wick, cut it to the center, make a triangle, and there's one of them already. Now the wick has to come from below. And then when you get it up through, I suggest that you crinkle it, fold it, ball it up, whatever, a little bit, so that it won't pull back through. And then, yes, that's right, Christina, check to make sure that it's going to reach the bottom of the beaker. Right, so now we're going to get into the periodic table. And ahead of time, I emailed you 2 sheets of periodic table and one that's all filled in. And we'll get to those later in the talk.
Okay, and just for those who are interested, there is our filter paper.
Beautiful. So we're going to do a quick review of material that we went over last week, assuming that you haven't committed it all to memory. The atom. All matter is composed of small particles called atoms. 3 different parts. Protons, which have a positive charge, mass of 1 AMU, or atomic mass unit, and they're located in the nucleus. And the electrons, which are negatively charged, they have no relative mass compared to the proton and the neutron, and they're located outside the nucleus. And we have the neutrons that have no charge, they're neutral. Neutrons are neutral. Protons are positive. Fortunately, with these shields, I don't end up spitting on you. Neutrons have a mass of 1 AMU, and they are located inside the nucleus. The electrons travel in different energy levels, and the lowest energy levels are the ones closest to the nucleus. As you get further away, requires more energy. The electrons can take in energy and become excited. Happy electrons. They get excited and they jump up to a higher energy level. And then when they come back down to the lower energy level, which is called the ground state, where they start out, then the energy is lost, often as light. And we talked about the Bohr model of the atom and showing the nucleus and the electrons in their energy levels or orbits. We talked about the atomic number. The atomic number equals what? As you found out on your worksheet.
The number of protons.
Yes, the number of protons. And the mass number is
The number of protons and the neutrons.
excellent. Protons plus neutrons. And then the isotope number is remember, we had that whole table of isotopes.
It's also the mass, correct?
Yeah,
So protons plus neutrons.
yes, exactly. And it's called the mass number. Okay? Now, one thing students often don't realize, when you talk about isotopes, every is isotope. Different isotopes have different mass numbers, but if you're talking about boron 10, boron 11, then each one of those is an isotope, even though most of it may be just one particular isotope. Some element math in an ion, the number of electrons changed from the neutral atom. See, isotope means different numbers of neutrons in the same element. Ion means you've changed the number of electrons, so you have a charge. The ion charge is the difference between number of protons and electrons. So if you have calcium plus 2, that means although you've got 20 protons, you lost 2 electrons, you only have 18 electrons.
David, can I get you to step back?
And then with fluorine with the -1, and one of the things you may notice in chemistry, we never bother to write the ones. So it just says negative. And fluorine with a -1 has 9 protons, as normally. If there weren't 9 protons, it wouldn't be fluorine. And it has 10 electrons. In order to have that negative charge, it had to have extra electrons. One of the things I liked on those of you who turned in your homework, nobody wrote fluorine. It's fluorine, U-O-R, instead of O-U-R. So I'm proud of y'all. We use element notation. In this case, Z represents the atomic number, the number of protons, and the superscript A, written before the Z, is the mass number, protons plus neutrons, and then X, the element symbol. That's backwards, David. I'm sorry. Z is the element symbol, and X is the atomic number. My error.
My teacher made a mistake.
Not the only mistake I've made, but I'm surprised I made that one. That's a really bad one for a teacher to make. So here we have a element notation. And what's the element?
Zinc.
Zinc. Very good. Whoops. Okay, the atomic number is 30. The mass number is
65.
good. And how many protons?
30.
30. Good. Number of electrons?
30.
Pardon?
30.
30, yes. It doesn't say anything about it being charged, so it's got to have the same number of electrons as protons. And the number of neutrons?
35.
Excellent. 35. You have to subtract the atomic number from the mass number. Isotopes, as I said before, atoms of the same element that differ in mass due to a difference in the number of neutrons. So boron 10 has 5 neutrons, boron 11 has 6 neutrons. To get that number on the periodic table, which is never just a whole number, it's got a bunch of stuff with the decimal usually. Well, that's the mass is an average mass of all the isotopes. It's what's called a weighted average, based on how many of that isotope exist. What's its percent abundance? And you can, given the data, you can calculate what that should then be. So the average atomic mass becomes the mass number times its percent abundance, plus for the next isotope, its mass number times its percent abundance, plus for the next isotope, and so on. That's why those numbers are not just whole numbers. Boron 10 is 20%, boron 11 is 80%. That's the amount that exists normally. And so their average is 10.8 AMUs for a weighted mass. Some terms you need to know. The ground state is the state of rest for the electron. There's uranium. It's got a lot of electrons, and they're in a variety of energy levels. An excited state is the position the electron moves to after taking in energy. If it absorbs energy, it jumps up. And when an excited electron drops back down to its ground state, it gives off that energy as light. And you can actually use that to identify what element it is. We said before, the electrons are in energy levels. They're fixed energy electrons. It's in halfway to an energy level. It's always all the way there. And they're made up of orbitals. We talked about those before. They're usually described as regions of space where there's a high probability of finding that electron. It's based on probability calculations, a lot of calculations. And electrons will always fill the lowest possible energy level first. The electron is happy when it's at lowest energy. And you can never have more than 2 electrons in any one orbital. So the s orbital, there's only 1 in each energy level, so you can only have 2 electrons in any energy level that are in s orbitals. But the p orbitals, there are 3 of them in each level. In drawings, they're represented as x, y, and then z coming out through the paper. With 3 of them, you can have up to 6 electrons in one energy level. D orbitals, there are 5 per level, so you can get 10 electrons, because each orbital holds a maximum of 2. And the f orbital, there's 7 in each energy level that has them, and so you can have 14 electrons in the f orbitals, and you're going to see later why that's significant. When we talked about the shapes of the orbitals, I said the s orbital is like a sphere. That's the way I think of it. The p orbital looks like a peanut. And since there's 3 of them, it looks like it's shown there in the diagram. The d orbitals are weird, especially the one that looks like a donut with a ball above and a ball below. But that's in somewhere in that orbital are 2 electrons. We don't know where, but we know it's there. And then the f orbitals look sort of like flowers. And like I said, I've never been able to find an artist who will combine all those for me so that I can see what it looks like to have all of those in one energy level. All the S, P, D, and F. So electron configurations are very important for this, and we're going to see how. It shows how the electrons are distributed into their orbitals. It's basically the address for the electrons. And a lot of students are taught how to figure out which electrons are in which orbital using the electron hotel. And I'm not going to go into detail about that because there's a much easier way. But that's the way most students are taught. And you just go follow the arrows and fill up the orbitals. Now, I sent you all a blank periodic table for the elements, and we're going to see how we can use that. So, electrons, the arrows represent the filling order for the electrons in the orbitals, starting from the lowest diagonal arrow and working your way up. But don't worry about that. There's an easier way. So, this is the way the orbitals fill. And quite frankly, with my students, when I give them a test, I put that information on the test without the superscripts, because they have to know that S can be 2, P can be 6, D can be 10, F can be 14. But as far as the filling order, it's not what you might think of logically, because it goes 1S, 2S, 2P, 3S, 3P, 4S, and then it comes back to 3B later. And that's because the energy is better if, when they fill the 3 Ps, go up to the 4th energy level for the next 2 electrons, then come back to fill the Ds. So it gets a little weird. But like I said, I never make my students memorize that. So after 6S2, if you use that electron hotel, you'll see it goes 4F14, followed by 5D10, followed by 6P6, followed by 7S2. But like I said, I don't believe in memorizing stuff, mostly because I'm very bad at memorizing. I'm good at understanding, but I don't like to memorize. So, how would we write the electron configuration for these elements? Neon, aluminum, oxygen. We're going to skip that for now. Okay, we'll give the answers. 1S2, 2S2, 2P6. Neon has what atomic number? You got a periodic table in front of you.
8, 10.
8? I don't think so.
10.
Yeah, 10. That's what it says on my periodic table anyway. So you just start filling up 1S, 2 electrons, 2s, 2 electrons, 2p, 6 electrons. Oh, there's 10. So that means that's neon. Aluminum with 3 plus means that you lost 3 electrons. So you end up with 1s2, 2s2, 2p6. Notice, now neon is a noble gas. So when something forms an ion, usually it then has the electron configuration of a noble gas. And so aluminum with the 3 plus is the same as neon, and oxygen with a 2 minus is also the same as neon. They want to be like the noble gases, because noble gases are happy, happy atoms. And the rule is everybody wants to be like the noble gases, to be happy, happy atoms. The production of light. Electrons are stimulated by energy. They jump up from that ground state. Ground state's the lowest energy level they can have, to an excited state with the higher energy level. And then when they move down from that excited state to the ground state, they release a packet of energy called a photon in the form of light. And this is the different lights emitted for different changes. And the thing is, though, you can have an electron jump up, say, to 7s2 and then drop all the way down to 2p6. So you can get a wide variety of different colors produced that way. And that's how we can identify atoms with the spectroscope. And with telescopes, looking at the sun, they can see what elements our sun is made of. So, the most important tool in chemistry is the periodic table. You go into any chemistry classroom or laboratory, there should be a periodic table in there. It's very, very important. And actually, you actually find them in biology classes too, even physics classes, because it is important. Dmitri Mendeleev, an iconic Russian, very unusual man, had many accomplishments, had many, many children, and he's credited with the creation of the periodic table. Now, in reality, there were a lot of people who came up with ideas for the periodic table. But he came up with something that was really important, as we'll see in a moment. A lot of the discoveries that were made technologically, for example, being able to accurately determine the atomic mass of an atom, of an element. When they finally got it to where they could accurately determine that, it helped them to figure out better where to put elements into a table. Now, the reason Mendeleev wanted a table was he was teaching chemistry, and he wanted a way to help his students see the relationships of elements to each other, how properties varied regularly, or what we call periodically. Mendeleev got credit for the periodic table because he made the most important contributions to it. One was he put elements in the table based on their properties. Now, a lot of people were doing that, but they were putting them in the wrong place where the properties didn't line up because it just didn't look right to them. But Mendeleev left holes in his periodic table. He said, you are going to find an element that goes here. It comes after silicon, and it just hasn't been discovered yet. But these are going to be its properties, and he went and named it ecosilicon. Eco meaning one more than. So he made these predictions, and later, frequently, they found the elements that fit those properties. Not always. He was wrong on some of them, like he believed in the ether as an element. Not ether the gas, but ether in the air. So he was correct a lot of the time. Oh, that was his table there. Periodic law means that when elements are arranged in the periodic table, there's a recurring theme. It matters what column they're in, it matters what row they're in. Periodicity means the arrangement of elements based on common characteristics. The horizontal rows are called periods. The atomic number increases as you move to the right in a period. Now, he did not organize his table, Mendeleev, by atomic number. He organized it by atomic mass, and that meant the elements ended up being in the wrong place, actually. And partly because some of the information just wasn't available. And later there was another man who said, hey, let's use atomic number, that's going to work better. And he was right. The vertical columns are called groups, or they're called families. Both are used. The atomic number and there's a line that didn't show up there, and I don't recall what it is. Atomic number and mass of the elements. Well, I don't know. So we're going to be looking at periodic trends, how things change on the periodic table. And we're going to look at three special ones. One's called electronegativity, just because we like big words. Another is ionization energy, how much energy it takes to knock off an electron or to gain an electron. And the third one is metallic character. So, electronegativity is the need or desire for electrons that an element has. How much does it want to have an electron, to gain one or to lose one? An element with a high electronegativity has a greater desire for electrons. It wants them badly. An element, conversely, with a low electronegativity is going to have a low desire for electrons. If two elements have an electronegativity difference, because we like to combine these long words, and electronegativity difference, we also like abbreviations. We call it the END. If the END, when you take two elements, look up their electronegativities and subtract one from the other, then you get their END. And if that's greater than 1.7, that means they'll probably form an ionic bond. And the greater it is than 1.7, the stronger that ionic bond. Conversely, if it's less than 1.7, they're going to form a covalent bond. But be aware, some textbooks use different numbers than 1.7. I prefer to use what I think is a much easier method. If you have a non-metal and a non-metal, it's going to make a covalent bond. And if you have a non-metal and a metal, it's going to be an ionic bond. Much easier to do very quickly. You're not always going to be 100% right, but you're going to be close. So where are the metals? I gave you a periodic table, and there's a red line there showing a zigzag staircase. And so I recommend that you make that on your periodic table, the one I gave you. Draw the staircase. It's going to go between boron and aluminum, then drop down between silicon and germanium, and so on, and it keeps dropping down like a staircase, as is shown in the screen. Everything to the left of that line are metals. Everything to the right are non-metals. But those that are on the line, now not if they just touch a corner of the line, but if they're on the line, then they're called a metalloid. So they have some properties of metals and some properties of non-metals. Now, there is an exception though, because aluminum is on that line. And aluminum is definitely a metal. It is not a metalloid. Some people draw the staircase a little bit differently because of that, but I've always preferred to do it that way. And hopefully the people at home printed out the emails that I sent them so that you've got a periodic table to draw this onto also. The second thing that we want to look at is ionization energy. Ionization energy is a measurement of how difficult it is to take an electron from an atom. Some atoms want to give away electrons. They're happy to. Some of them, they want to acquire electrons. So they're not happy to lose them at all. And that's the ionization energy. The harder it is to take an electron, the higher the ionization energy is going to be. And that varies across the periodic table, vertically and horizontally. Last is the metallic character, how metal-like an element is. And what is the character then of a metal? We talked about that previously. Metals are malleable, they can be shaped. Metals are ductile, they can be drawn out into wire. Metals have good electrical and heat conducting properties. Copper wires make really good for electrical. Aluminum wires not so great. For a while it was cheaper, and so putting a lot of aluminum wire in houses, and then the houses started catching on fire and they decided that might not be the best idea. Metals are solids at room temperature with one exception. Who can tell me?
Gallium?
Mercury?
Gallium melts in your hand, but at room temperature, it is still a solid.
Mercury?
Pardon?
Mercury?
Yes, exactly. Mercury. Fun to play with and dangerous too. But that is the one solid, one metal that is a liquid at room temperature. Metals have a high luster, especially if you take something like sodium. It combines with water in the air, it also oxidizes, so it is dull looking, but if you slice it until it reacts, you'll see that it's quite shiny. It has a high luster. So I gave you a blank periodic table, and that's so you can have this information. Don't write on it yet, because I'm going to take this, which is really not nice, but we're going to make it even better. So you see, as you go up the periodic table over on the left, the ionization energy increases and the electronegativity increases also. As you go to the left on the periods, the metallic character increases. As you go across the top to the right, the ionization energy increases and the electronegativity increases until you get to noble gases, because the noble gases you can't ionize. Metallic character decreases as you go down. Of course, increases as you go to the left. We can take those 4 arrows and turn it into one. That I would like you to put on your blank, because you see that if you're going up and to the right, so going up or going to the right, your ionization energy and your electronegativity increase until you get to the noble gases. Noble gases, the electronegativity is very high. There's no ionization energy because you can't ionize it under normal circumstances. And then you'll notice going up and to the right, your metallic character decreases. I don't know what you're pointing to.
I'm trying to get you to move towards the screen.
Towards the screen. Oh.
You keep edging forward.
Uh,
Not good.
yeah, I'm used to being close to my students.
Sorry.
Okay, give everybody a minute to finish copying that down. So those trends are very important. When we get to the very end, I'll stand out of the way because there's a whole bunch of pictures that I had to put on the whole screen. Now, one thing I wanted to mention, wait, I'll bring it up later. It'll fit in better. Looks like we're caught up. The modern periodic table. And I found one online that has all the elements, because now all 118 elements have been named. And that's important. And one of the reasons that's important is the next element that's discovered, it is thought, is going to reach a plateau where they don't disintegrate quickly. And if that's so, then further discoveries of elements will be things that will stick around. Because a lot of those in the very high numbers down there, they're gone fast. Parts of a second. But if we make some that stick around, and they're going to have unusual properties, and we're going to be able to make brand new things out of them that'll be really cool. And that's great. Now, I wanted to point out, on the left-hand side, at the very top, you have hydrogen. And on the right-hand side, you have helium. Now, they're both only putting electrons in the first energy level. So helium, in reality, could be put right next to hydrogen. In some periodic tables, they'll actually put it in the middle and then draw to the right and an arrow to the left to indicate that helium could be in either place. And it makes sense because it's filling the s orbital. So columns 1 and 2 are putting their valence, or outermost electrons, in the s orbitals. Now, I suggested that you might want to have highlighters, 4 different colors. And unfortunately, I brought some for people here to use, but I could only find 3 colors, and somewhere in my house there's 50 highlighters, but I could not find them. I'm just not that organized at home.
The cat
So
probably
you
got
could
them.
highlight, or maybe draw a square or a rectangle around the first 2 columns, and then label that as the S block, because they're filling S orbitals. So it's the S block. And that means there's certain properties that all those elements are going to share. So they are highly active. And there are great YouTube videos where people are throwing cesium into a bathtub of water and blowing the bathtub apart because it is so reactive. And you'll see ones that say they're showing francium plus water, but they actually just show a nuclear explosion. If you added up all the francium in the entire world, it would be about the size of a baseball. So it's hard to get a lump of francium anywhere. Okay, so the first two columns are the S block. Column 1 has a name. It's called the alkali metals. So if you would write that somewhere.
Excuse me, I'm going to change your mic because you're dropping out. Okay, try now.
The column 1 are the alkali metals.
And will I go turn you up?
Alkali metals. Column number 2 has a somewhat similar name. It's called the alkaline earth metals. So the family is the alkaline earth metals. So please label column 2 on your periodic table. And then if you go all the way to the right-hand side, columns 13 through 18, except for helium. You could highlight those in a different color, or draw a rectangle around them in a different color. But all of those are putting their outermost electrons, the valence electrons, into the p orbitals. So that's all of them. They're all filling p orbitals. And those columns are named for the top element. There's the boron family, the carbon family, the nitrogen family, oxygen family, and then the last two have special names. So column 17, they are called the halogens. Such as you see in halide lamps. Anyone remember what I said column 18 is called?
The noble gases.
Yes, very good. The noble gases. Oops. They are not the winners of the Nobel Prize. It's spelled differently. Nobel Prize is N-O-B-E-L. These are N-O-B-L-E. They're noble because they're like royalty. They don't mix with commoners. Rarely does anything make a compound with one of the noble gases. They are all happy, happy atoms, and they just won't mix with anything. If you combine columns 1 and 2, the s orbitals, and 13 through 18, the p orbitals, we call that the main group elements. In lower level chemistry classes, a lot of the times they talk mostly about main group elements, because when you get outside of that, things get weird. Now we haven't talked about columns 3 through 12. Those are elements that are putting their outermost electrons in d orbitals. So this is called, we have the s block, the p block, and the d block. So d orbitals are being filled by the elements in the d block. So it's important to differentiate that on paper. S orbitals, D orbitals, S block, D block, P block. Right now I'm holding a periodic table much like the one you have, but there's something missing. What's missing off this?
The lanthanides and actinides.
Couldn't quite hear that.
The two bottom rows.
That's correct. Where are the two bottom rows? Well, if I take these clips off, there they are. That's where those rows actually go. They're in between the S and the D. Anyone know why they put them down at the bottom like that? Because this doesn't fit well on an 8.5 by 11-inch piece of paper. So it's only because it fits better on a piece of paper if they put those two rows down at the bottom. Okay? So those two rows are called the F block. They are filling F orbitals all the elements in both of those. I went backwards, didn't I? Yeah. So the first row has a name. It's a family, and it's called, excuse me, the lanthanides, which is the first one in that group. Lanthanum. And the second row, its family name is actinides, because actinium is the first one in that row. And as I said, that's the F block, filling F orbitals. So how can we use the periodic table to write electron configurations much more easily? Well, I've written up at the top what the entire electron configuration sequence is. The first number is the energy level, then is the letter for which orbitals are being filled, and the second number is how many electrons are in there if it's completely filled. So if something is in the S or P block, the energy level number for that final valence electron is going to be the same as the row number. Now, this periodic table does not have numbers on the rows, so you need to add those. 1, 2, 3, 4, 5, 6, 7, 8, 9. So, for example, if I said, where are the valence electrons for magnesium? Well, you look on here and you find Mg, magnesium, and it's in the third row. So that means its last electrons are going to be in 3, and this is the S block, so it's 3s, and it's the second one over, so it's 3s2. And so its total, complete electron configuration would be 1s2, 2s2, 2p6, 3s2. Yeah, that's right. Now that works fine for the S and P blocks. When you get to the D block, it's just a little bit different. Okay, it didn't give that. Oh, there it is. Okay, for the D block, and what you can write right above D block is D block equals row number minus 1. So let's take a look at manganese, Mn. It's right there. It's in the 1, 2, 3, 4th row. But it's in the D block, so we have to subtract 1 from the row number. That gives us 3. So that means the final electron is going to be in 3D. And then you count over within the D block. 1, 2, 3, 4, 5. The final electron is going to be 3D5. So writing the total electron configurations go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. And that's the electron configuration. That's the address for that final electron. That's the electron configuration for that element and no other element. And that's going to determine how that element is going to react with anything. Now, the bottom block, the F block, right below that, F block equals row number minus 2. For the F block, you have to take it minus 2. So let's say we look at Lawrencium. That's Lr. It is the very bottom, the right-hand corner. So count the rows. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 minus 2 is 7. So that's going to be in the 7F. And then we have to count over.
David,
1,
can
2,
I get you to step to your left, please? You're stepping. People at home can't see you.
Sorry. So it's in the 9th row. We subtract 2, so that's 7. It's in the F block, so the final electron goes in 7F. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Nope, I did that wrong. Oh, that's because technically lanthanum and actinium don't get counted there. So Lawrencium is actually the 14th one over, and so it becomes 7F14. I need to go back later and look at something and make sure I didn't mess that up. I did. And I know why. It's not in the 9th row. I'm sorry. We just said a little bit ago. It fits in between here. So it's actually in the 7th row. So it's 7th row minus 2 is 5, and it becomes 5F14. That's Mendeleev's original periodic table, laid out a little bit differently than what he did to start with. But like I said, he was the professor who was trying to come up with a way for his students to understand how the elements were related to each other and the periodicity. And of course, as you can see, there were a lot of elements that hadn't been discovered yet, an awful lot. And there it is shown like a modern periodic table showing the actual elements that were known at that time. And you can see where he left holes in the periodic table. Now, there are other periodic tables in use for a variety of reasons. And this one is a circular periodic table. And that works because in reality, this thing wraps around like this. And the atomic numbers increase appropriately, and it's not really a circle, it's a spiral. Let's take a quick look at the lab. Yeah, it's not moving yet. Okay. That's the one problem with this. When I do it at school, my students set it up, they leave it. At the end of the day, I take them apart. This is instructions on making a spiral periodic table. That's available on the web. And this is a different version of the spiral periodic table, again showing how it's all related, increasing atomic numbers, and where different families are. And that's one made out of paper. And that's a Chinese periodic table. Any of you read Chinese? I've had Chinese students, but they don't read it. I can speak it, I can't read it, so they don't know if it's right or not. So I pulled it off the internet, and they claim that's a Chinese periodic table. So I have to take the word for it. The atomic radii periodic table, the size of the circle indicates how big the radius of the atom is. The periodic table by abundance on Earth. So the more space the element takes up, the more abundant it is on Earth. So what are the three most abundant elements on Earth?
Carbon, hydrogen, oxygen.
Hydrogen, carbon, and oxygen. Yes, those are the most abundant elements on Earth. And hydrogen you find in a lot of minerals and organic compounds. Carbon is in all the organic compounds and a lot of minerals. And then oxygen in the air and combined with most of the elements on Earth. The abundance of the elements in the universe. And you can see that hydrogen is the most abundant element in the universe, followed by helium. And then everybody else comes along, with some of them actually being quite rare. Mineral abundance in humans. What are you made of mostly?
Calcium?
Yeah, calcium. Why? Where's all that calcium in you?
Our bones.
Yeah, in your bones. Bones and teeth, and then you also have calcium ions in your bloodstream.
Shouldn't there be carbon on the list?
They did not put carbon because these are supposed to be inorganic. And carbon is organic. And that's why you don't see hydrogen and oxygen also. because they would be there in great abundance. As a matter of fact, I've read 60, 70, 80% of your body is made up of water. So there's hydrogen and oxygen. But that was a real good point. Thank you. The endangered elements periodic table. What are the elements we're running out of? You'll notice that helium is high up on that. We're running out of helium. Well, we were. The largest deposit of helium is in Amarillo, Texas. And they have the helium monument there. If you've ever played jacks, where you throw a ball and pick up jacks, well, the monument is shaped like a huge jack, about 30 feet high. And each leg is a time capsule. And they've already opened one. I don't remember what years they were, but they've opened one up already and had a lot of interesting things in there. More recently, within the last 2 years, helium has been discovered in some other places. And now we think we're not as bad off as we thought we were. Because there's actually a need for a lot of helium, not just for blowing up birthday balloons. Although that is one major use of it. But a lot of reactions are done in helium because it's a noble gas. It's inert. It doesn't react with anything, almost. But anyway, it's important to keep track of what elements we're running out of and where they come from. Because as trade gets cut off from certain places, we lose some very important things that are needed. And the Kansas periodic table. Most people think Kansas is a bit backward, and so they have the periodic table with the 4 elements of earth, fire, air, and water. And I found the periodic table of elements featuring Final Fantasy. I don't know why they chose where they put the characters, but I don't follow Final Fantasy anyway. And I've seen this one several times. It's kind of small, it's about 7 by 5 inches. And they say that each element is embedded in the lucite. I'm sure they do not have the radioactive elements in there. They just have something to represent them. But I saw an ad for it yesterday. It's on sale for $25. But, no, other way. My favorite is the periodic table table. And it has cubby holes there that you can open them up and have the elements down inside. This is made and sold by a man who, I won't think of his name, and he wrote 2 apps I've got on my computer that I love on the periodic table of elements. And you can't buy it. I forget how much it is, a few $1,000s, but he only sells it to museums and colleges.
My wick, but it hasn't started going out into the paper
Okay.
yet.
We're going to let them go overnight, and I'll check them tomorrow morning. And I'll take them out if they're finished. They just take a lot longer than I would like them to. I think if I would have used water with water-soluble markers, it would have gone a lot faster. But that's okay. Would you like to make any predictions? What do you think is going to happen? Assuming it works.
Well, I assume the colors will go out, but as for the RF, I have no idea which
Oh,
one's gonna
don't worry
be
about
bigger.
that. Yeah,
I don't know which one's gonna go further.
yeah.
Is it?
Don't worry about that. The real question is I have, do you think any of them will make more than one color? Or to put that another way, why do you think I said everybody had to use black? If black is a composite, it's made up of more than one color. So you'll end up with different colors. They go different amounts because they have different polarities. So they go different distances. Basically, your composite colors, um, those of you who do art, what do you call complementary? Complementary colors are often made up of more than one color. And so they will spread out more. So we'll just let that go and see what happens. Another way I have done this is taken some dirt and water and salt and added some food coloring and mixed it all up and gave it to my students and told them there was a poison in it. And they were to separate the water from everything and then run the chromatography to see what kind of poison it was based on the color. And how would they separate out the dirt? Give you a clue. The first thing they do is mix it up in some water. Then what would they do to get the dirt out of it?
Use a filter.
Pardon?
Use a filter.
Yes, exactly. Run it through a filter that'll pull out the dirt. How can you get the water separated from the salt? Because you filter it? No, it's a solution. Salt dissolves in water, and so it's not going to filter out. It passes through any filter.
Could you evaporate it out?
Pardon?
Evaporate it out?
Yep. Boil it, that'll drive off the water. And if you do that with a condenser coil, it'll save the water for you. It'll turn it back into liquid. For that experiment, I wouldn't do that because you could end up separating out the food coloring. So instead, we just go ahead and get rid of the dirt and then go ahead and use it, the water with the salt in it, because it wouldn't affect the color. And then do the paper chromatography, and the color will show up, and whether it's several colors or whatever, and I always had a key for them telling them what color each poison was. So, just trying to make things more interesting for them. Any colors, any questions on this? Why do we do it? What is the purpose of chromatography?
So you can separate the components of the composite part that you put in initially.
Absolutely, that's right. That's why we did it. Okay? And so we hope that that's what we'll see. And when you do the calculations, you get RF. You can often use that RF to identify an element, compound. It would require that you know something about what was there to begin with. But yeah, the RF can be used for identification. Now, I mentioned before with electrophoresis, you run a current and separate, like say, amino acids or immunoglobulin fragments, and then you turn it and run it the other direction. And that's how they came up with the Southern blot, which was named for Dr. Southern, who came up with it. And then somebody came up with another way of doing it, and so they called it the Northern blot, simply to be the opposite of the Southern blot. And then another one that's used these days is called the Western blot, different ways of doing it.